this with the new system.
Right, okay. Hello!
A learning curve for us.
And that goes in there, does it? Okay. Hello, everybody! Are you all signed in? Okay.
Right, I'll leave you be.
Now, there's only two things you need to know about me. One, I'm not Chris Pryor. And the other thing is I don't work either in Aztec RAL or in Trinity College, Oxford. So that whole slide is now invalid. Right. Now, Chris, who should be giving this lecture, he's kindly not been here, but he did give me his lecture notes, and there's an inconceivable number of them. There's 56 slides, which I'm supposed to cover in 2 hours, and I'm supposed to do all this lot, which is really quite impressive. Now, I think hands up who's got a physics background. So we're 1, 2, 3, 4, 5, 6. So more than half. Okay. So for you lot who should have done, have you all done a course possibly in your second year called Special Relativity or Relativity? Okay. So for you lot, this will be a refresher. And then who's engineering? Okay. You lot, it will be something more akin to a very brief overview, where at least you'll have seen some of the names, and then if you need relativity for your PhD, if you're starting to do something like beam dynamics, where relativity is vital, you're going to have to learn all the stuff. But there's no way in 2 hours I'm going to be able to cover all the stuff you need. So think of it more as sort of an introduction. That one doesn't work. Page. Does this one work? Oh, yeah. Okay. There are some books. Relativity's been here a while, so nice people have written books about it, which is good. I think. Where are we? Oh yeah, here you go. Chris Pryor's book, probably a good one. But you probably want to stick to the things called special relativity. So there you've got Rindler and Woodhouse. I think they're both quite good. The Mesner, Thorne, and Wheeler. There's a lot of general relativity in there, but that's okay because it's that thick. So the first little bit will probably be about right. It's good if you feel that you want to build your muscles up and do lots of weightlifting. You can carry Mesner, Thorne, and Wheeler with you everywhere you go. Okay. Okay. Historical background. Who's heard of the Michelson-Morley experiment? That was the interferometer, where they measured light. They were trying to measure the speed of the luminous ether. Who's heard of that? Basically everyone that's done a relativity course. I'm always impressed because relativity is the only course where you spend the first two lectures talking about a theory that's wrong. Every other course you just start off with what we now believe to be the correct theory. But the most interesting thing about the ether and the Michelson-Morley experiment is Einstein, when he wrote down his theory of relativity, didn't know about it. He doesn't reference it. He makes no statement that he knew about what the result was. So he came up with relativity purely from electromagnetism and Maxwell's equations. So anyway, so there's a bit of irrelevant background and so on. Okay. So, some ideas of relativity. There's such a thing as inertial frames, as in Newtonian mechanics. You have an inertial frame where there's no gravity. We don't deal with gravity at all, and there's no you're not accelerating. Okay, and you would know. How would you know you were in an inertial frame? Presumably you would look at all your neighbouring particles and they would all be staying where they were. Okay, you'd all be floating together. You wouldn't feel. We know. How do I know I'm not in an inertial frame? You obviously aren't used to my lectures because I do pick on people when I'm teaching undergraduates. So what can I feel as, I'll start over here. What can I feel that tells me I'm not in an inertial frame? Yes, I can feel the pull of gravity, so I'm not in an inertial frame. And of course, if I drop things, they move relative to me because they're not being resisted by the reaction force of the floor, which is doing a very good job of not making me fall into the middle of the Earth. So that you can ask the question, well, hold on a minute. Most particle accelerators, at least the ones that you're going to be designing, they're on Earth, and they're going to be subject to gravity. So why can we ignore gravity?
Things are moving so fast, doesn't it? Like the effect is so tiny.
Yeah, the effects are tiny. There are some experiments that are so sensitive you do have to worry about gravity, but on the main scheme of things, it's fairly irrelevant. Okay, I'm going to miss out that lot and talk about transformations. Okay, so in fact I'm going to go straight on to space-time diagrams because I love these. Now so what is a space-time diagram? Well, space-time diagram, you draw time going up the side and space along here, and you then take a moving particle. Now, moving particles in special relativity, well, we assume for the moment that it's only travelling in a straight line at uniform velocity. So that's going to look like this. So unlike most diagrams you see, where normally you write x as a function of time, here we've sort of reversed the coordinates round. So this thing is moving. This is sort of, you can think of this as today, tomorrow, the day after that. And this is a snail. So today he's here, tomorrow he's probably over there, just outside the door. He's not moving very quickly. Okay, now here have a associated axis corresponding to his, so this is his position, and we call that t prime. Okay, he'll also have an axis that corresponds to his x. Okay, now in if I said that this was like a rotation, well, if I rotate in space, okay, so I'm going from here to here, you would expect it to rotate like this. But because special relativity time is different, okay, it turns out that it goes not rotating, preserving the angle, but rotating, preserving that this line here is remains at 45 degrees. Now, what's the significance of this line? This line is something that moves 1 unit of time in, no, so 1 unit of space in 1 unit of time. And you might think, well, that's 1 meter a second or 1 kilometer an hour. Well, we have to choose special units. We have to choose units where 1 unit of time is 1 second, and 1 unit of space is, does anyone know? Well, this is what a ray of light does. So this is 1 light second. Which is about 300,000 kilometers. So if we put our tick marks like that, then a ray of light will be this line here. It travels 1 light second in 1 second. Sounds reasonable for light. And obviously it will travel 2 light seconds in 2 seconds. Now, our snail now is actually moving remarkably quickly. It's actually going to move what? I don't know, what would you say that was about? Maybe a third, approximately. So it's moved 100,000 kilometers in 1 second. So I don't want to see that snail. Okay, Unfortunately, you wouldn't see it for very long. It sort of whizzed past you. Anyway, the point being that this this line here, this corresponding line must be the reflection about it, so that if I take a tick mark here corresponding to 1 second in this frame, okay, then that, and I draw the equivalent of this box, that's going to look like that, because that line there is parallel to that line there, and it's going to look like that, and this is 1 light second, just call it 1 ls. Okay, so in this frame, light travels 1 light second per second, just as it does in this frame. And this is the universal constant in special relativity, that the speed of light is constant. Okay, everything else has to change in order to keep the speed of light constant. Okay, now, and that's what this is saying. It preserves the wavefronts for the speed of light. Okay, well, how do we get around that problem? How do we alter, what do we have to change in order that the speed of light remains constant? Well, what you have to change is the time and space, okay? How we measure time and space. And you see that according to this diagram, my light second here, my point here, that is going to be over here somewhere. It's going to correspond to a different time later on. This is the famous twin paradox and clocks, okay? So according to this, there's something called a gamma factor. So if I sort of explain the symbols, what's going on here, we're moving, we've got 2 frames moving with a velocity v, okay? On this diagram here, this angle here is v. So in 1 second, if I draw that down here, that's v times 1. Okay, so it's moving at a velocity v. That's what this line represents. We divide by c. Okay, that's the speed of light. So that corresponds to this line here. We square it. Okay, and then we've got 1 minus the square of it. Now, if my v is anything human, anything that we might physically be able to do with ballistics, so with a macroscopic object, I can't remember what the fastest macroscopic object we can generate, but it's certainly only, I don't know, tens of meters a second or something, or hundreds of meters a second, and we divide that by the speed of light, which is 300,000 kilometers. I don't know, it's a lot. So this is a tiny number, and then you square it, so it's going to be even smaller. This is going to be very close to 0, and so I've got 1 minus something that's very close to 0, so this is really approximately 1, and 1 over 1 is 1, so gamma is approximately 1. So for any human speeds, gamma is pretty close to 1. But if there are things that we can accelerate, fortunately, to relativistic velocities, and they are little things, subatomic particles, and some of you work in that industry. Okay, all of you work in that industry, so you need to know what happens to subatomic particles. And in most accelerators, v, well, we've got certain different accelerators. If we're doing something like a klystron, okay, v might be 10% of the speed of light. Who's dealing with klystrons? Okay, so 10%, so this is 0.1, square it, 0.01, so this is 0.99, square root of 0.99 is 0.98, okay, so gamma will be about 1.02, okay? You could probably ignore that unless you're doing very, very delicate mathematics. But start coming along to an electron at, well, I can't say CERN. What's the fastest electron machine out there at the moment? Don't know. But anyway, there you're looking at, oh, I don't know, 0.9999 the speed of light or something like that. So this sort of, this is very, very close to 0, and then 1 over it is going to be a hefty number. And if we we've got TeV for, if we take the LHC, okay, well, the way you get it is you divide, you take the energy minus the rest mass. Is it minus the rest mass? No, plus the rest mass. Okay, divided by the rest mass. Now, I need to put a c squared in there. But normally they quote particles in EeVs or GeVs, which is already an energy. So we talk about the mass of a proton being 1 GeV. Well, what's an EV is? It's a measure of energy. Okay, so and that is your gamma. Okay, so if we take the LHC, we've got 7 TeV plus 1 GeV. Well, that's going to be such a small difference, it's not really worth talking about. Divided by 1 GeV, and that will give me my gamma as approximately, where did I get to? Yep.
7,000.
7,000. Okay. And since 7,000 is this expression here, okay, we can see that with a bit of manipulation, 7,000 is 1 over square root 1 minus b squared over c squared. Square everything up. What we've got here, 14 times 10 to the 6 equals, hold on a minute, where are we doing? 1 over 1 minus b squared over c squared. God, never do calculations like this. Yeah, so we divide that by that. So we've got 1 minus v squared over c squared equals 1 over 14 times 10 to the minus 6. So that v squared over c squared is 1 minus something really small, 10 to the minus 7, which tells me that v is very, very close to 1. Okay, you couldn't even work that out on a calculator. Okay, it's going to give me, so v is, what's that, 1 minus 10 to the, actually that's not so bad, 1 minus 10 to the 4-ish times, okay, it's not too bad, it's 99.99 the speed of light. But these are protons. Protons are heavy. They require a lot of energy to accelerate them. If you did the same with, if you did a 1 TeV electron machine, this would be 1,000 times bigger. Makes everything a lot bigger. So they're much closer. Okay, so so we've got these relationships. Now these relationships are just what I've drawn up here. No, not there. What did I do? I'm going this way or that way. There you go. Oh yeah. Okay, so this is my t prime, which is a function of x and t, and this is just a constant. This is just a constant, so this tells me it's a straight line. Likewise, my x prime, which is this line up here, is a function of t and x, and then y and z. Well, y could come out like that, and then z. Any ideas? Okay, I need an extra dimension to try and put that somewhere. Okay, so we have to suppress y and z because I've only got 2 dimensions to draw on here. Okay. Right, so you can see from here that these tick marks corresponding to 1 second in this frame are not in the same place as the tick marks corresponding to 1 second in this frame. And this is the sometimes called the twin paradox. Who's heard of that? Hey, you not heard of the twin paradox? No. So the twin paradox is, hold on a minute, if time slows down if something's moving, what happens if I shoot off to Alpha Centauri and come back again? Okay, which twin would be older? So twin paradox, 2 twins, one of them goes on a nice long space journey, the other stays where it is. But according to I can't resist it. I'm sorry. At this point, I always put up 2 members of the audience as demonstrators. So you can be my particles. Well done. Well done. Okay, so you're twins, obviously. Okay, you can do the journey to Alpha Centauri, which is over there. Okay, now if you watch your twin, okay, what does it look like she's doing?
Getting smaller.
Getting smaller and moving away from you.
Yeah.
Okay, so he's moving relative to you, you're moving relative to him. So according to special relativity, he should be younger than you, and you should be younger than him. Okay, and this is the twin paradox. And then you come back again, okay, and which one is the younger? Well, if we draw it on a space-time diagram, that's all right. This is your line. Okay, what's your name?
Sonal.
Sonal. I'm going to misspell that.
AL.
AL. Okay. And you are?
Stu.
Stu. Okay. Now here's Alpha Centauri. Okay. You've flown out to Alpha Centauri, and then you've come back again. Okay. And you can see something's happened when you're at Alpha Centauri. You changed your motion. Okay. Now, now let's compare this to rotation. So you both have to stand here. Okay. Sorry about this. And okay, in the same place as close as you can. Now, you're going to move 2 steps forward, and you're going to move 2 steps at 45 degrees. Okay, 2 steps. Or was that 2 steps? Now, that doesn't quite work. You want to move a little bit forward, but not as much as that. Okay. Now, the equivalent of the same time, okay, is if you look out your window at exactly 90 degrees, okay, are you in front of or behind Sonal?
In front of.
Okay, and if you do the same, are you in front of or behind Stu?
Behind.
Damn. If you come forward a little bit, right.
Sorry.
Okay, so now he's in front of you and you're in front of him. Okay, and you can see there's no contradiction because you're in different places. Now, if you carry on moving, let's say our goal was here. Okay, so you move 2 more steps. You've taken 4 steps to get here. Now you have to turn. You have to turn the steering wheel, okay, and move like that. Now you walk there, and you're going to take slightly more than 4 steps, okay? And there's been no contradiction, okay? So not only have I, thank you, round of applause to our, okay. So not only was there no contradiction, okay, but it answers, so if there is no contradiction, it answers the question about the twin paradox, okay? Now, diagrams are all very well and good. Eventually, if you're going to treat problems in anger, you actually have to do some maths, and so you need these equations called the Lorentz transformations to tell you what's going on. Now, for some reason, Chris thought it was very important that you knew that Lorentz actually did some drilling. So there you go. I don't know why that was. Okay, there's Lorentz, there's Minkowski, there's Poincaré. These are some of the mathematicians and physicists who did it. Now, here's a very, very brief derivation of these transformations, and the key result is, well, the input is you have to assume that the one coordinate system is linearly, is just a linear relation to the other. That is, it's as though you're multiplying by a matrix. Okay, so you see that if t, x, y, and z are all 0, then so is t prime, x prime, y prime, and z prime, and that's equivalent to this point here. Okay, and then you just take linear relations. That's because this bit here is a straight line. Okay. Then what you do is you assume that the speed of light is the same in both, and therefore you have that ct squared equals x squared plus y squared plus z squared. That is the line ct squared minus x squared minus y squared minus z squared. That is the formula for a ray of light. Okay, if we look on here, okay, this line here, that's the line x equals t. Okay, but if I was to put a y in there, okay, then I'd have to make x squared plus y squared equal to t squared. Okay, so this line here then becomes, anyone remember what that is? What happens if I take this and I swivel it round? What do I get? A cone. And this is called the light cone. Okay, and that light cone is given by this coordinates, by this function. Anyway, so you map, you start off with that. You create this equality. You fiddle around with the numbers, and out falls the Lorentz transformations. Actually, talking about the cone, it's always a nice thing to play with. Okay, so I'm going to do my best at drawing 3 dimensions down here. So we've got 2 dimensions like that. You can imagine that one's in the plane of the whiteboard. This one's coming out. I've got time moving up here. And I take this line here. Okay, and there's my cone. I've got another cone downstairs here. Oops. Now, relative to this point here, all these points inside the cone, that's the future of this point here. I can get to in principle, to any point inside here. In order to get to the surface of this cone, I have to travel at the speed of light. Okay, so I can only get to points if I happen to be a photon. And last time I looked, I wasn't a photon, fortunately, I suppose. And then this area here, this volume out here, that is elsewhere. Okay, I can't get to any point out here, and furthermore, I can't be influenced by any point out here. Okay, so if a supernova goes out off here, okay, I'm not going to know about it until the light from that supernova has reached my timeline. Okay, let's talk a bit about simultaneity. I knew this would happen. I knew that. I love this lecture, and this is the one I always give. And then I looked at Chris's slides, and I think, well, I'm just going to stick to Chris's slides. I'm not going to give my lecture. But if I take 2 points which are simultaneous in this frame. Now, simultaneous means that they've got the same time frame, the same time coordinates. So we'll take this moment here. Right, so I'll take that point A and that point B. Okay, they are what are called space-like connected. There's no way that A can influence B or B can influence A. But I could generate them if at some point in the past I do something and I set up these two little explosions, say here in New York, I'm not a terrorist, okay, but I set them to go off simultaneously. Now, in principle, I could do that. I could put clocks on them, they'll blow up. So here's A in New York, B in London. It's close enough. And they will blow up at the same time, and they'll be space-like connected. So we can say that the explosion in New York did not influence the explosion in London. But they had to be generated at some point in the past. Now, in the T frame, they're simultaneous. But let's look what happens in the T prime frame. Okay. Now, to get to the T prime frame, I have to draw parallel to this line here. So I draw that here and down here. And you see, oops, it's this point here, that in the T prime frame, B, which one occurs first? Where did I get to?
Oh, B.
B. So B happens before A. Okay? So if I were on this frame, I would think that B happened first. Okay? And then I can draw another frame moving in the opposite direction where A happens first. Okay? So there's no concept of simultaneity for different space-like points in special relativity. But as I say, there's no twin paradox. Actually, for T prime to see these explosions, he wouldn't see these explosions. He would have to wait for the light from these explosions to reach him, and he's out here. So if we draw the light rays coming from here, he would see, which one would he see first? Where did we get to? A. Why is that?
That's the light that reaches his.
But what's the significance about, if you like, the distance from him to A and B? Hey, sorry?
A's closer.
A's closer. Okay, so he would actually see A first, but that's purely as a result of A being closer. But in his time frame, B has happened first. Okay. Where have I got to? Okay, here's the Lorentz equations in their full-blown three-dimensional version. Okay, they're quite nasty. Fortunately, most people I know who do relativity don't really do much with the Lorentz transformations. Okay, they're have I run over? No, it's past, isn't it? Right. What they generally use is invariants, and we're going to come to those in a moment. Okay, now, not only do we have time dilation, we have length contraction. Okay, what happens if I view something moving? It looks like that thing is shorter. It looks like things contract, and we can see that here. Okay, on our space-time diagram. Good. I like space-time diagrams. Okay. Now I'm going to draw a new one because that one's getting a bit busy, and that's got some numbers on it. There we went to Alpha Centauri and back. So. This is just going to be awful for anyone watching it online. You're really privileged to be here. I hope you feel privileged. He made me ask questions. No one's allowed to do that. Not once I've graduated. Okay, so here's obviously my space-time diagram, Tx, and here's my light. Okay, so that's going to be green light this time. Here's my moving person, T primed. Here's my moving, the corresponding X to that one. Now, let's say, so this is my train. It's always trains. Here's my train moving. That's, well, I've got to work out which is that the front or the back of the train, but Now, here's this is parallel to this. Now, which one of these is the front and which one is the back? Okay, well, I always have to think about it, but if we draw this one going right down there, you can see that this line here has crossed this person's timeline, okay, before this one. So this is the front of the train. This is the back of the train. Okay, now here's the length of the train as far as here's the length of the train as far as the person on the platform, not moving, is concerned. Train length. Okay, but here's the length of the train. Length. Okay, here's the length of the train as far as the train is concerned. Okay, and it turns out they're different and they're related by this gamma factor. Okay, and I can never remember which one's which. Okay, it turns out that it contracts. Now, it might not look like it contracts because this length here looks longer than this length here, but you actually have to draw a hyperboloid to get it. Where's my red gone? Here we are. And I think, if I'm right, I think my hyperboloid does that. Okay, and this is a line of length 1 in the different frames. Okay, this line of length 1 gets more and more asymptotic to there. So as I go faster and faster, the line of length, my ruler gets longer and longer in this board. Okay, so it looks like the thing's contracted, and now you get that wonderful thing of man with very long ladder runs into shed. Okay, and the shed is smaller than the ladder. Okay, so I'm running with my ladder into the shed. Okay, but according to the shed, my ladder has contracted. Okay, so it can enter the shed, and then I can close the door on the shed. Okay, and it's inside the shed. So according to the shed, the ladder is smaller than the yes, according to the shed, the ladder is smaller than the shed, so it can fit in. But according to me and the ladder, the shed has contracted. Okay, so the shed should be smaller than the ladder. So what's happening? What's the contradiction? This is one of Einstein's other famous contradictions. Now, fortunately, I've already drawn the space-time diagram for this. It's all right, I've got through 11 of 56. Okay. No, yes. Okay, I'm doing plank, train, and platform here. Okay, so you can think of the platform's not moving. That's a frame of the platform. And here's the frame of the train. Okay, now, have I done this right? No, I've not done it right. Oh. I have to do this there. That's it. So ignore that line. Okay, so now let's look at this. According to the platform, it's the black line, the train is that long. Okay, and the platform is that long. So the platform is longer than the train. Train, black. Okay, but let's have a look what happens with with the train, okay, that's this blue line, okay, that's the frame associated with the train. Here, the train, so this one the train was shorter than the platform. Here, the train is longer than the platform. Okay, can you see that? So the length of the train is the green one, the length of the platform is the black one. Okay, so in the frame of the train is longer. In the frame of the platform's longer. But there's no contradiction. Why is there no contradiction? What's obvious on here, what's happening is we're measuring the train at a different time. Okay, the back of the train is measured at the same time according to these two, but the front of the train is measured at different times, and the front of the train's moving. So it's not surprising that what we measure as the length is different. Okay, now I thought, well, trains and platforms are all very well and good. What's that got to do with me? I'm an accelerator physicist. Now, I'd like to point out that is not a sperm. Okay, you will find out what that is. It was only after I drew it I realised that looked just like it. Anyway, here is my lab. Okay, and here is my bunch of electrons. Okay, now bunches of electrons move very, very close to the speed of light. My red line is my light. Okay, this is my back of my electron, and this is my front of my electron. Okay, and for the back of the electrons to send a signal to the front of the electron, okay, well, it emits a signal at this point here. That signal has to travel all the way along this red line until it crosses. Okay, now if this is electrons, we're talking of gamma factors of, what's it, hundreds of thousands. So we're talking very, very close. This is very, very close to the speed of light. If you actually drew this, you wouldn't be able, you'd need a magnifying glass to distinguish this. This line up here is crossing maybe days or weeks later. Okay, well, the entire time the electron is in, say we built a linac, so it's literally traveling in a straight line. The entire time that the electron's in the linac is, what's it, microseconds, isn't it, or nanoseconds. So the back of the bunch never gets to talk to the front of the bunch. Okay. What's more, what's more is that the back of the bunch, in the frame of the bunch, this is really, really long. Okay, and as far as electrons concerned, so a bunch is what normally I always think of them as knitting needles, or I think it works out. You should think of protons look like knitting needles and electrons look like sewing needles. If you draw the dimensions of a bunch, so a bunch of electrons is typically that long and a bunch of protons is typically that long. Typical machines, I don't know. Anyway, so ooh, I've come back. Hello. God, I've not been moving. Oops.
It's only just stopped.
It's only just a second stopped.
No, but I kept having, every time I refer to this, I'm supposed to do the press a button, and I've not done that. But what I'll do, for the people who aren't here, hello people who aren't here, I'm going to get Laura to take photos of these, okay, and you should be able to see it. Oh, God. I knew I'd forget. Right, here is the time, the space line for the electrons, and this is really long. So the electrons think that they're a long way away. Okay, so the front of the bunch, the back of the bunch can't talk to the front of the bunch. But you might think, well, that's okay, but surely the back of the front of the bunch can send a signal to the back of the bunch, because I'm a bunch of electrons. I'm at one at the front. I can send a signal really easily, just traveling at the speed of light, from the back of the bunch, from the front of the bunch to the back of the bunch. Okay, but now we get onto one of the weird things in how do electrons send electromagnetic signals? Well, Is this supposed to be the field due to an electron? Okay, and it moves, all the information goes in the direction that it's moving. Okay, it's like a little searchlight. Okay, if I'm moving in this direction, all my electromagnetic fields, which normally spread out around me, they're all concentrated in my direction of motion, and there's no information being shone backwards. Okay, so even though in principle it could send information that way, it doesn't. Now, what's going on here? Ah, I know what's going on. Right, so connect, come back, please come back. What's happened now? Content. Hello, hello. Oh God. Right. I'm not seeing anything now. Do something. Hey. Well, at least they're getting this on there. So, okay. So time dilation we spoke about. Trains we've spoken about. You see, I was actually doing this. Okay, so these are all on the slides. For those people who aren't here, you can read up this. Now, this is obviously doing it using the maths, but for those people who need the maths, you'll have to read this up. Okay, but the most confusing thing with the maths, which makes it so hard, is that it's trying to work out which one is moving relative to which is the one that time contracts, which is the one that time dilates, and so on, which is why I find the space-time diagrams so much more easy to use. They always talk about muons. The fact that you can see muons on Earth was a big surprise. Actually, it wasn't a surprise because everyone was expecting it, but muons, typically muons in particle accelerators in the 1960s weren't, so they were generated in, not the accelerator, but in interactions, and they could measure their lifetimes, and they were, I think it's microseconds. Okay, and you work out how fast a muon can travel, how far a muon can travel, and basically should only be able to, so they're 2 microseconds, so they should only be able to travel about 600 meters before decaying, but we knew that they were generated in the upper atmosphere, and we could detect them on Earth, and that we should not have been able to detect them on Earth. But if you put the gamma factor in time dilation, so it's a direct test of time dilation. But this is all a old hat now. If you look at muon accelerators, okay, why would we want to use a muon accelerator? What's a muon got that an electron hasn't, or rather more of? Mass. Okay. If we could make a muon accelerator, it's more or less the same weight as a proton, or that sort of order, but it's much cleaner. It's clean like it's not made up of anything, so it's clean like an electron, and yet it's got the mass like a proton. But the problem is, well, first of all, you have to create them, and then you've not got long to play with them. You've only got a few microseconds. Okay, so you've got to accelerate them as quickly as possible, so that the time dilation can make them. So you've got some that are still in when at the interaction point. So it's really quite a challenge. But actually, accelerating them isn't such a challenge. The real challenge is cooling them down. So that means accelerating them all in a nice beam, because you don't generate them from a nice, just heating up a bit of hydrogen. You've got to generate them, in some complicated reaction. They're all flying in different directions. They've all got different energies. And so you want to accelerate them all in that direction, and then you've got to cool them down so that they're all nice. So it's quite a challenge, and that's what mice is all about. Who's heard of mice? Muon something Coulomb something. You know what it stands for?
Muon isolation Coulomb.
Yeah, experiment. But it would be brilliant if they could do it, and that could be the next big thing in accelerators, if they never, or the one after the next so-called next linear collider, or I can't mention the words ILC because that's a no-no, but they're still talking about it. They just called it a different name. So we've done space-time diagrams. That's good. When you start doing these things in anger, then you start having to write things in matrix form. So we can take this Lorentz transformation and we can write it in this form, a matrix form, and that's called the Lorentz matrix, the position vector. And the thing about it is, oops, you've not done it. All right. The thing about this matrix here, which is L, is that dear. Is that L transpose equals G, where G is this matrix of -1, 1, 1, 1, and a bunch of zeros. Okay, and the set of all Lorentz transformations is given by this relation. So if you want to know what all of them are, you can do it in this algebraic way, and that allows the Lorentz boost in any direction and so on. But we've also got who recognizes this relation in terms of matrices? Yep.
Identity matrix.
That's the identity.
Yeah.
That's the transpose of A. With A times the transpose of A. Okay. These are the sort of things I love. But anyway, this is a rotation matrix. Okay. This is the equivalent of a rotation but for space-time. Okay, so these are related. And we see we've got the identity as a sub-bit here. Okay, so if we take our A to look like this, 1 and then a bunch of zeros here, and then we have an R. Okay, this bit here is a rotation. So all the Lorentz transformations include all rotations as well. So if you need to think about all those things, that's one way of doing it. Okay, so we've mentioned that, here we are. So this relationship here, okay. Oh no, here we're doing it on vector. Okay. If we take a vector, that's our t, x, y, z, we can construct this quantity, x dot x. Okay? And, you see, that's a mistake. That's supposed to be g there. I got it right. If I consider this quantity here, t squared minus x squared minus y squared minus z squared, that's an invariant, which means that in every frame I look, it gives me the same number. And the use of invariants is really a really powerful tool for analyzing, for actually getting numbers out. And in fact,